Thanks, Dr. Gable, for that introduction, and good to see most of your faces, some of your faces. Hi, everybody virtually who's getting to watch as well. So yeah, I'm quite excited to talk today about some of the research that I've done over the past year, and I'm going to add a few caveats here at the end. So putting a new spin on magnetic topology, my sabbatical study magnetic skyrmions. So I will tell you that I knew like 3 of those words 1 year ago, and I'll explain why in just a second. So I chose to take a year off from teaching to study magnetic skyrmions, and that's probably a weird question or thought to do. So as Dr. Gable pointed out, I spent the last 10 years at Creighton thinking a lot about kind of optoelectronic materials. So that could be, for example, photovoltaic applications, transparent conductors, different types of sensitizers for dye-sensitized solar cells. And so we had this kind of strong push in this kind of device physics. We've also spent a lot of time in the directed self-assembly of block polymers to develop nanostructures in a very organized way and using directed self-assembly. And we got to do some inventions and really fun things there, inventing this apparatus and really trying to revolutionize what we could do with directed self-assembly. We've also spent a lot of time dealing with dental materials, dental interfaces, dental surfaces. This has relied heavily on the technique known as atomic force microscopy, where we were able to look at things like cellular attachment, adhesion, kind of surface structures to see how things osseointegrate or integrate into the oral cavity, how cells attach to them. And so, again, we've kind of been all over the place in terms of a group over the last decade here at Creighton. And so I also, at the same time, was working quite heavily within the Creighton's energy technology program, where I was primarily focused on dealing with the solar aspects, solar technology aspect of that program. And a lot of fun things happened there. We took 3rd place the year before my sabbatical in the Solar District Cup out of 62 teams across the country. And so career was going pretty good. And then sabbatical comes around and things have changed. So now I had this kind of question of why would I study magnetic skyrmions and what should I do next? And ultimately it came down to a fundamental shift in what I wanted to think about for my career and what I wanted to think about for what I wanted to be, doing for the next, let's say, 10 years of my life. And I got interested in this idea of magnetic skyrmions for some of the reasons that Dr. Gable pointed out. I am a trained physicist, that's where I got my doctorate. But sometimes I feel like I fit better with engineers, and I play a lot with engineers or material scientists. And so you'll notice that a lot of the projects that I've taken on historically have been in that bent. The other thing I've noticed that this is the last year of the energy technology program. So I'm having to redefine myself as somebody beyond energy technology, but magnetic skyrmions, right? So computer data storage is kind of projected to be about 15% of the world's consumption of electrical energy within the next few years, right? So big data is a big energy hog, right? And so I've become, acutely aware of sustainability and trying to be more energy efficient. And it was kind of curious to me to think about how we could potentially make this a more efficient process. And that was one of the reasons that brought me to magnetic skyrmions. The other one is that there was something that was really just fundamentally new to me. I thought that the underlying physics was interesting. I mentioned I don't know many of these words, or I didn't know them. I didn't know really what topology meant. I heard it all the time. I didn't really know what skyrmions were. I had heard of them before. But these were really new things to me, so it was a real challenge that I wanted to take on. And I hope that you find it interesting. So my warning to the faculty who I saw were online and also in the room: don't try to run 2 labs or help run 2 labs at once, especially if they're in 2 locations. Dr. Seeger, you'll probably have feelings about that. That was a bit intense. And the commute to Lincoln starts to get pretty old after after a while. So for those of you who don't know, I became an affiliate faculty member at the University of Nebraska. So this is partly a COVID thing. I wasn't allowed to be at UNL unless I worked at UNL. And so I became an affiliate faculty member there so that I could actually have access to the building. I also became a user at the Nebraska Center for Materials and Nanoscience, a certified user. So that was a big piece of it. And so I got to play with a really great lab at UNL. Of course, we're all wearing masks and doing all of our COVID safe stuff. And that was great. Loved it. And I had 2 graduate students working with me, and we were working on a lot of these spin textures that I'm going to talk about today, as well as surface acoustic waves, which I'm going to talk about today, and a lot of magneto-optic measurements, which I will also talk about today. So I worked with those 2 graduate students. I brought on somebody you might recognize, Grace Dirks, last summer, who helped with that group, and you're going to see her name pop up a lot in this presentation because I stole a lot from her to put this presentation together. So while all that was happening, I also was running the lab here at Creighton, and so thankfully we got 3 publications out during my sabbatical based on that work. And so we were still continuing with solar technology stuff, and we were dealing with dental material stuff and all that. All these things are still happening. And so for that, I'm gonna point out Max specifically. So Max marks into Prince. Without him, I think this whole thing would have fallen apart. So thank you, Max. You really held down the fort while I would be away in Lincoln. And I would also say that I'm very grateful to audiobooks from that community. So let's talk a little bit about magnetic storage. I think that's a good place to start because I don't think a lot of people understand magnetic storage very well. And then I want to bring its relevance to topology. And then I'm going to bring that together to talk about why I'm studying skyrmions, what a skyrmion is, and then how we might be able to manipulate skyrmions for data storage applications. So when we think about a mechanical hard disk, and so this is different than a solid state, which I'll get to in a second, what we're really talking about is a magnetic hard disk. So something that has magnetic elements to it. And so if you've seen the inside of a hard drive, you might see something familiar like this. If we zoom in a little bit further, when we talk about magnetic storage, what we're really saying is that let's take a handful of grains of magnetic material. And by grains, I mean something that's about 8 to 10 nanometers in size. It's basically like a little clump of magnetism. And we take a pool of about 50 to 100 of those, and we polarize or magnetize them in one particular direction, and we call it a 1. And then we magnetize them in the opposite direction, and we call it a 0, right? And so this is the idea of magnetic storage. And this has been around for quite a while, right? We've thought about this quite a lot. There have been some, really great advancements in storage, even in the last kind of 10 to 15 years. For a long time, we used longitudinal magnetic media, which meant that the grains all pointed in the plane of the film. We learned, again, about 15 years ago, that if we went to a perpendicular geometry, we can improve the areal density by a lot. And so now we have much more dense hard drives, and hard drives went from being a few megabytes or something to like maybe a couple of gigabytes, and now it's obscene values, right, of multiple terabytes. And that really came about because of this type of transition. The problem now is that if we want to keep going smaller, and of course in the magnetic storage game, size, speed, and stability are really the paramount things that we think about. There's this kind of trifecta of problems that we have to address. So these bits need to be writable, right? So we need to actually be able to make them a 1 or a 0. But at the same time, they can't be so writable that thermally they can just flip, right? We would like our stuff to be stable. We would like it to stick around for a while. And then we add in this third piece of it also needs to be readable, right? So there's some size limitations to it, and all these things are kind of happening that ultimately lead to size limits that we're really bumping up against when we talk about it from an engineering perspective. And so conventional multi-grain media is kind of starting to see the end of its lifespan in terms of taking this any further, because how much smaller can we actually make these grains and maintain this thermal stability? So I actually jumped into this game about a decade ago, and we tried out patterned magnetic media, which is that we actually patterned isolated islands that would just be a single bit, right? And so now we don't have these two bits touching each other. We're going to talk a lot about grain boundaries today. We don't have as many grain boundaries to deal with, which is this transition from up to down. And we can isolate everything. And so we did this in my lab a long time ago, 10 years ago. And we got into this game and we made these perfect islands. But what we found was that this had huge scalability issues. It became really difficult to think about how to actually implement this much further. There are people who still think about this, but for the most part, solid state drives were kind of on the rise. So this kind of started to fade into the background. And so cool solution, but maybe not the best solution. So size, that's the first issue that you could potentially tackle in magnetic storage. The second one would be speed, right? So we would also like to be able to access our stuff faster. And so certainly solid state drives have made a really big impact on that, right? As we transition to solid state drives, things tend to be faster, but ultimately we still live in a world where we store everything in one location and we work with it in another location, i.e. the random access memory, the RAM inside of our computer. And so there was a new paradigm that was introduced in about 2014, which was known as racetrack memory. And the idea behind racetrack memory is that you use something that is magnetic, but you essentially have a wire. And so it does have this kind of electronic feel to it. And you actually pass encoded bits through wiring. And now we can actually make these things travel much faster and much more efficiently. And so your RAM and your storage become essentially one and the same. So imagine a world where you don't have moving parts, but you also have instant boot times. It's magnet, so it can be rewritten essentially forever and endlessly. We can rewrite it multiple times, which isn't true of solid state drives. And it turns out it's much more efficient. And this is actually something that caught my attention. It's about 300 times more efficient than traditional RAM. And the reasoning is RAM is just this very kind of volatile thing, right? So as soon as we turn our computers off, RAM goes away, right? RAM says, no, I'm done. It has to go into hibernate mode, or it has to go into sleep mode. It has to dump everything into a storage place, the hard drive, to remind itself where it was before. And it's true, solid state drives have really helped that, but we still have this issue that we're always working within the RAM. And so just to keep a computer idling is about 300 milliwatts, to give you an idea of what that looks like. If we were able to do this in a very non-volatile way, i.e. using magnetism, we could essentially take that away down to about a milliwatt. So that's that 300 times more efficient. And so this technology was developed by Stuart Parkin. Those in the magnetics world look at him like he's a rock god. He developed a lot of the things that have made computers awesome. He worked for IBM for many, many years. He's not there now. He's actually at Max Planck because he wanted just to focus on science, not so much the engineering aspects. He actually just very, very recently won the King Faisal Prize for Science, which for those who don't know, a physicist gets it one every 4 years. So it's kind of a big deal that he got that prize. And I mean, if you think about the things that he did at IBM, he improved aerial hard drive densities by a factor of 1,000 while he was there. He was the inventor of MRAM, magnetic random access memory, and now the inventor of racetrack memory. And these things led to him winning that prize. I did put in this quote of his former boss at IBM who wrote, "As with all of Parkin's inventions, I have no doubt that racetrack memory too will be a great success and have a major impact on society." In particular, Stuart Parkin pointed out in his speech for having won this prize, is that he said not only is it a potential solution for things like data storage and manipulation, but this actually has really important implications for quantum computing technologies. And so if you start reading about Skyrmions in literature, you're going to start to see overlap with quantum computing as well. All right, so size, speed, stability, and this is where I come in, right? So generically speaking, storage applications based on magnetism are incompatible with things like domain walls, I'll explain, magnetic textures, I'll explain, which interrupt what would otherwise be a homogeneous magnetization, right? So if I have a magnetization this way and this way, they necessarily have to come together and we have to flip from one to the other. And this is a potential problem when we talk about magnetic based storage applications. So hold this thought for a second, because we're going to talk a lot about domains today. But before we get into them, I think it's probably important to take 5 minutes and refresh what we know about magnetic materials. So for those of you who haven't taken kind of maybe an upper level like E&M class or solid state class or something similar, magnetic materials are just one class of material, of course, but it really is just the fact that different materials respond differently to an external magnetic field, right? And so they primarily break down into 3 types: diamagnetic, paramagnetic, or ferromagnetic. And ultimately, that has a lot to do with what's happening with the electrons in the individual atom. And the one that's probably most important for us in this conversation today is the ferromagnetic case. And in the ferromagnetic case, we see atoms that don't have a shared electron. So they typically come in pairs, right, where one is spin up and one is spin down. But if we have an asymmetric pairing, and so we maybe only have one, now we have this kind of tiny little magnetic field that essentially has some memory to it. So if we actually apply a magnetic field to it, it kind of remembers where it was, because the magnetic field internally polarizes it in that particular direction. And so that's the type of thing we're going to focus on today. So if we look at ferromagnetic behavior, it really falls upon this thing called the exchange interaction, which basically looks at the dot product between 2 adjacent spins or atoms with lone electrons. And it says, hey, you should align yourselves with one another, or anti-align. But exchange interaction typically leads to alignment of these 2 things. And so this is what leads to ferromagnetism, that these things tend to want to align with one another. And this is typified by looking at what does the magnetization internally do as a function of the external magnetic field. And so I have paramagnetism, diamagnetism, all of those on there. And so you'll see paramagnetism and ferromagnetism tend to do whatever the field is doing, right? They're going to kind of follow along. If the field gets positive, it goes positive. If it goes negative, it goes negative. Diamagnet does the opposite. But importantly for ferromagnetism is that you see that it has this opening of a loop, and this is called hysteresis, which means that it actually has 2 values for a single magnetic field, which implies that it has some memory to it, which is why ferromagnetism becomes critically important when we start talking about magnetic memory. So let me break this down a little bit further. So if we look at a magnetic hysteresis loop, we can put on a field and we can saturate it so that all of the spins tend to point in one particular direction. And so we saturate them all in a particular direction. And for a ferromagnet, if we take away the magnetic field, i.e. go to 0, it might retain it. And we call that term remnants, the remnant magnetization. Now, if we want to then switch it the other direction, we need to go to some reverse field, which is known as the coercivity, and that's how much field it takes to then reverse that magnetization. So what I'm going to show you down here is a video, and this is a video that was taken in our lab with one of our new pieces of equipment. I'll explain in a second. And it kind of shows you what happens when we go from one saturation to the opposite saturation. And so what we see is that a magnet doesn't just switch, right? A magnet switches in this very, what I will refer to as domain-like way, right? Where we start to see pools of magnetism of the opposite direction. So in this case, white is pointing at you, black is pointing away from you. And we see that pools start to emerge, nucleate, and then they grow as we're trying to reverse the field. And as we reverse more and more and more and more, it gets darker and darker and darker and darker as these domains grow and take over. And so this is how ferromagnetism works. So let's talk about these things that I've referred to as domains, right? So if we think about a magnetic material that's ferromagnetic, we're all probably pretty familiar with a kind of bar magnet, right? We have the North Pole and the South Pole. And it turns out if I apply an external magnetic field, it's more than happy to do this because the field will stabilize it in this configuration. However, if we look at the stray fields, the magnetostatic energy density is huge, right? These stray fields are huge and they extend out all over the place. And so nature doesn't like this. Nature would like to minimize the energy that's associated with all of these stray fields. And so as we remove the field, to kind of help keep it in that state, it'll break up into what we call domains, right? And so think of how we've jumped from A to B here. By this side switching south to north as opposed to north to south, we've minimized these stray fields a lot. So the magnetostatic energy density drops a ton because it's become more and more confined to this little region. If we break it up even further, we can make this even smaller, right? We can take magnetostatic energy density and just keep dropping it and dropping it and dropping it. The problem is that every time we do that, we create what's known as a domain wall. So this transition from one direction to the other direction. But the exchange energy, which says that these things should be aligned, is saying, no, 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 no. We want everything to be aligned. Well, this is clearly not aligned. So we have this competition between these two things where we want to minimize the magnetostatic energy density, but we also want to minimize the domain wall energy. And so depending on the right mix of these two different things, we might have these kind of blobby-like domains, or we might have these really, really well-defined striped domains. And it's really just a kind of definition of how these two terms are interacting with one another. And so at this point, I think it's time that we need to start talking about domain walls. So domain walls typically come in these kind of two different flavors. There's actually others, but these are the two dominant ones. One's known as the block wall, the other one is known as the Yale wall. And ultimately, it's how does the magnetization switch from one direction to the other, right? And it doesn't just happen perfectly abrupt. So there's three knobs, if you will, or three terms that we want to think about when we're developing or kind of a construct of how these domain walls form. So the first one is the exchange knob. We've already seen this one. This is S dotted with S of the two different spins. Remember, this is the thing that's trying to keep everything aligned, right, in a ferromagnetic way. We have the anisotropy knob. And so this is basically saying that it might have a preferred crystalline axis, it might have a preferred direction because of shape, but basically there's some preferred direction where the magnetization would like to point. And in some sense, I think of this as being maybe like a clamp on either side of the domain wall. How hard is it going to be clamped in a particular direction, knowing that the spins themselves are going to be held together through the exchange. And the final piece, which might be new to a lot of you, is what we'll call the DMI knob. Right? The reason I'm saying DMI is it stands for Jastrzębski-Maria interaction. So, and I'm never going to say that again. But that actually is the critical piece of everything we're going to end up talking about today, which is basically allowing for the possibility of spin canting, right? And so as opposed to spins being perfectly like parallel or anti-parallel, this DMI term actually allows for some rotation, and I like to think of this maybe as a spring within these two clamps. And so this will actually cause the chirality or the handedness within this domain wall region. And that's one of the things we're really going to play with in this work. So if we want to do this and actually turn it into something like racetrack memory, right? So racetrack memory is literally making domains that have domain walls and being able to push these things through a wire, right? So these are the things that we're going to be playing with. It turns out that some work has been done, including by, this is the group that I work with, Dr. Aiden group at UNL, that you can push these domains down a wire. You can do it with magnetic field. You can do it with current pulses, so pulses of current, which create spin currents, or you can even do it with string, which we'll talk about in a little bit. So there's a lot of ways that this can happen. The problem that occurs, and this is also data from our Creighton lab, what you're going to see here is a bunch of wires and a big pool of magnetism here. So in this is going to be field pulses as you see this movie progress. And so if we watch these wires, so this one in particular, what we'll see is that, go again. Only one by one. What you would have seen, but it was hard to see in that one time around, is that these don't grow very deterministically, right? They're very stochastic in nature, right? We see them jump and then stop, and then jump and then stop, and then hold out for a while, and then have a big massive jump. So it's this stochastic nature that is a real problem, right? Because if I'm going to make a memory device, I need to know exactly where that domain is. I need to know exactly where that domain wall is at all times if I want this to be a viable strategy. Beyond that, there's this thing called Walker breakdown, which is basically if I pump a bunch of current into this thing to try and get it to move through spin currents, sometimes it'll just randomly flip. Maybe it hits a defect in the wire and decides to annihilate itself. So there's a lot of potential problems. So can we make a magnetic texture and give it motion in a wire that is deterministic? So to do this, I want to introduce the concept of topology. So topology is the study of any property that remains unchanged when you have some continuous distortion, right? That's the definition of topology. If we make some continuous distortion to an object, can we still maintain all of the same properties it had before? So in a simple example, right, we can think of a square and a circle, right? I can make small iterations to a square and turn it into a circle. So from a topological standpoint, nothing happened, right? They are exactly the same in a topological sense. Their job is to basically define inside of the circle and outside of the circle, or inside the square or outside of the square. That's their only job, right, from a topological standpoint. Now we can extend this further, right? So in physics, we talk about the spherical cow all the time, right? Well, from a topological standpoint, a sphere and a cow are identical, right? So if I take a cow and I only make continuous distortions to it, I can continuously distort it to be a sphere, a banana, a lemon, doesn't matter, right? I can do all of these things from a topological perspective. That being said, a sphere is never going to be a torus, right? We're never going to turn a ball into a donut through continuous changes, right? From this kind of topologically relevant method. And ultimately, it comes down to the fact that it has a hole in it, right? So if I have a balloon and I'm going to try and make some kind of torus shape, eventually I'm going to have to cut a hole in it, right? So in some sense, this becomes topologically protected, and that it's going to remain in the nomenclature is in its genus within topology. And so topology actually won the Nobel Prize of Physics in 2016. So this has been a really hot topic on physics over the last decade. So I like this problem, so I decided I would share it. So this is called the Hairy-Ball theorem. It was actually proven back in 1885 by Kerr. And colloquially, it's expressed, you can't comb a hairy ball flat, right? So if we think about a hairy ball, right, or the top of our heads, you're always going to create a cowlick, right? There's always going to be some singularity where you can't just keep combing, right? This is always going to happen. You're going to get tufts at either end, or something's going to happen. Well, a sphere can either be thought of as a three-dimensional ball, and we're only considering the surface, or a two-dimensional sphere, which is just the actual surface itself. Now, so it's impossible. This has been solved. It's impossible to comb it flat. However, if we change topology to the torus, which doesn't seem like a big change, from a topological vantage it really is, now this is a very easily solvable problem. You can easily comb a torus and get all of the hairs to lie flat. This will come up again in a second. The first problem to be thought about in topology, and I found this kind of in history books and found it interesting, is the 7 bridges of Königsberg problem. And so this was actually solved by Euler. And the idea was is if you had 7 bridges, can you cross all 7 bridges exactly once, right? And he proved that this is an impossible problem. You can't do it in this particular case. And it's thought of as being now a problem of topology, that it's really a topological issue. Until you can change its topology, have it turn on itself, or do some other type of weird topology things, this is an unsolvable problem. And so again, we start to get to this idea of stability. So I want to apply this idea of topology now to magnetism, and in particular nano-magnetism. So if we start taking an atomic view of magnets, we can start looking at changes in magnetization through the lens of topology. And this introduces us to the concept of what's known as a magnetic skyrmion, which you see here to the right. And let me talk a little bit about what this family of topologically interesting things are. So this one is probably most relevant to start with. So essentially, you're going to take this thing, which we might call a block point or a block sphere. And what you'll notice about this sphere is that it's always going to start and end in the same place as you go around any kind of line segment around this sphere. So we start at the top, we go to the bottom, we go back to the top. If I start over here, I go to the right, I go to the bottom, I go to the left, and I come back to the right. And so we define this as having a topological charge. Sometimes it's referred to as winding number that is quantized in some way, right? So that it always goes back to where it started. And so it has a winding number or topological charge of plus or minus 1. Now I can envision a variety of these block points that have arrows pointing in different directions. And so maybe they kind of curl around like this, or maybe they all stick out very radially hedgehog-like. And if I then peel them away and turn them into a two-dimensional object, which is what's trying to be depicted here, what I get is something that is topologically interesting because it has this topological charge of plus or minus 1, and could potentially be stable, and I'll explain this in just a second. But there are a variety of these that we could potentially play with. The two that I'm going to talk about today are nail type and block type, which, as you might recall, are the same types of domain walls we've already discussed. So if we look at this kind of more specifically, I'm taking this block point and I'm peeling it out to be a two-dimensional thing. If I look at some lines throughout this, what I see is this kind of winding throughout, but notice it has an exact winding number of 1 or negative 1, right? I start here, I move to here, and then I come back to here, right? And so, and it's going to always be that. It's always going to be exactly 1 or exactly the opposite, negative 1. And so if we were to plot this out in terms of angle, you see that it goes through a full 360 degrees. So the way I like to think about it is kind of like a vortex, right? So I mentioned this on like the first day of classes or for the grad students. So we see vortices in a lot of physics. So we see this in superfluids, for example. We see it in superconductors, and we refer to those as quantum vortices. And they're considered quantized topological effects, in those cases, defects. Now, magnetic vortices also exist, and much like a water vortex, which we're seeing here, to change its direction. And when I say direction, I mean chirality. Right now we have a clockwise spinning. If I were to want to change this to be counterclockwise, this is a really hard thing to do, right? You can imagine being in front of the sink and trying to frantically get this thing to start changing direction. So this starts to become a topologically protected thing. And you'll see here as it gets to the end, even the walls and the boundary conditions of the problem, they don't seem to have an effect, right? This thing just keeps on going, maintains its chirality all the way through. So it involves changes in topology to change its polarization or rotation. So it implies some stability or topological protection. So let me give you one example in one dimension, and then I'm going to show 2 dimensions in a second. So I've already shown this, but what if we don't have the full 360 skyrmion like 1D domain wall? What if we just have 2 kind of domain walls that have opposite chirality? Now notice if I'm the green, right? In this particular case, if I'm the green and I want to rotate this way, this side is like, okay, you're just coming with us. But if I rotate this way and I look to this way is also like, okay, come and join us, not a problem. So the green can flip and I haven't upset either side. Hopefully you track that. I haven't upset them, right? I'm just following exactly what they do. Now try and do the same exercise with the top one, right? If I try and rotate him, let's say clockwise, left side is saying, great, come on, come with us. Right side is saying, no, hold up, wait. Exchange interaction says you're trying to flip me and I don't like this, right? So I'm getting stuck. Now let's try to go the other direction. Right? Now if I try and go this way, clockwise, now this side is like, sure, you can come with us. That's going to track exactly with what we're doing. But now this side is saying, no, 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 no. You're trying to get us to spin even tighter than we already are. So this becomes a topologically protected thing. If we look at this in a full kind of Skyrmion way, we have our winding number of either 1 or -1. This is kind of how it looks from a graphical viewpoint. It turns out that it has a very similar topological counterpart, which we call a trivial bubble, and it has what's known as block lines in it. And because of these block lines, it's possible to have, through continuous deformation, which we talked about for topology, to actually make it go away. So it's not topologically protected. However, if we have this winding number of ±1, it requires a true change in topology to actually get to this trivial state, right, where it can annihilate itself. And so we have some stability. This is great. So what are the knobs for Skyrmions? Exactly the same as they were for a domain wall. Not surprising, right? So we took the one-dimensional view, it was exactly this, right? And so it's the exact same knobs, the exchange knob, the anisotropy knob, and this DMI knob. So what did we do? We had to think about how to deal with these knobs. So exchange knob is determined by the ferromagnet we use. And for us, we chose to use cobalt. So that knob is kind of done. We picked already. It turns out DMI is strongly dependent on what's known as spin-orbit coupling. And so you want something with a large orbital adjacent to it to create this DMI effect. And so we picked some heavy metals to go on either side of our cobalt, platinum, and tantalum. So these are high Z materials, really big orbitals, strong spin-orbit coupling to create this DMI effect. And what that leaves us is the anisotropy knob. And for us, it's really dependent on the shape of the ferromagnet. And so we're going to do this by changing the thickness of the cobalt. And so to do this, we did it with magnetron sputtering in the Nebraska Center for Materials and Nanoscience. And sputtering is a pretty straightforward idea. We take a vacuum system and we flood it with argon and we ionize the argon. These ionized argon atoms will bombard a target surface. That target could be cobalt, platinum, tantalum, whatever. And it's going to transfer its momentum, eject an atom, and then we'll collect it onto a substrate. So we have atomic scale resolution of growing our films. And so when I say it's 5 nanometers, I'm saying it's 5 nanometers, plus or minus, angstroms. And so it's quite good. Because of the way that this is set up, it's a conformal geometry, so we can actually produce wedges. And these wedges are going to be important for looking at thickness-dependent phenomena. So this is how we deposit them. And it turns out that if we grow cobalt on platinum, the cobalt will tend to have what's known as perpendicular magnetic anisotropy, or it's going to want to point perpendicular to the plane of the film, as long as it's sufficiently thin. As cobalt gets thicker, the spin-orbit coupling gets weaker throughout the thickness, and now shape takes over, and shape is going to tell the cobalt to be in plane. And so by making a wedge, we should be able to actually tune this anisotropy over large positive to 0 to large negative. And so that was our focus. To measure this, we used magneto-optic Kerr effect. Simply put, this is a light source that goes through a polarizer, a linear polarizer, and it impinges upon our sample and then comes back reflected and goes through a second polarizer. Now these two polarizers are crossed, and so no light should get through, right? No light should pass through these crossed polarizers, but the Kerr effect tells us that as we're reflecting off a magnetic surface, we'll see both a rotation in that polarization. We'll also see a change in the ellipticity. And so we'll actually get light through that second polarizer. So we just monitor the amount of light coming through that second polarizer, and we can actually map out what's happening magnetically as we adjust the magnetic field. This is the setup that we built downstairs. that is more like tabletop. And then we also built this inside of a microscope. Just think of turning this on its side and you'll notice it looks a lot like a microscope, where we have light coming down, reflecting off the sample and going to now an eyepiece as opposed to a signal detector. Thanks to Brad for helping me machine all the parts to make these things. So we developed some wedges successfully, thankfully. We were able to make sides that were thick and thin. And if we look at their magnetic behavior, they do exactly what we had hoped. If we start at the thin side, where the perpendicular magnetic anisotropy PMA should be large, we see very square loops, meaning that the film goes up or down, and that's it. However, as we got thicker and this started to fall in the plane, now it's like we're pulling it up and we're pulling it down. So we see this kind of more rotational motion. And we see a continuous change as we go from one to the other. And so we have a knob, right? We're able to tune the anisotropy independent of the DMI and the exchange interaction. And so we can determine thicknesses through X-ray reflectivity. We can determine crystallinity through X-ray diffraction and prove to ourselves that the cobalt is doing what we anticipate it to do. And thankfully, the magnetic behavior is consistent with being able to gradually change the magnetic anisotropy by moving along the wedge. So we can actually study what's happening and what is an ideal place to look for skyrmions. And so here's some hysteresis loops of some kind of critical positions. And what we found in this case is that we could potentially make skyrmion-like things, but they're not isolated skyrmions. They're these kind of wispy things that actually recently have been shown to be half skyrmions. And so I'm not going to get into half skyrmions, but that's what they are. It wasn't what we wanted. So we needed to take one step forward. But we were able to use our microscope to get a video of this thing switching. It's not great, but it's there. Where we could actually see kind of what's happening magnetically as we're trying to move these things around. So instead, we made multi-layered stacks. So by adding more and more layers, we're adding more what's known as dipolar coupling. And this will actually help stabilize the skyrmions. The problem is that they just keep getting smaller and smaller and smaller and smaller as this dipolar coupling gets bigger and bigger and bigger. The magnetic hysteresis loops show something that is really promising because it has this kind of pinched area in the middle, or what we call wasted. This is an indicator that we have a closed flux state, i.e. something that rotates on itself. For every up, there's a down. For every left, there's a right. For every angle, there's another angle. So when we take away the field, everything's rotated in on itself, and so there's no net magnetization. And so that's where this pinch comes from. So it could be an indicator of skyrmions. It could be an indicator of other flux-closed states. So we use magnetic force microscopy to detect these things. And so in magnetic force microscopy, it works just like atomic force microscopy, where we raster a cantilever across the surface. We pass a laser across its back, and we look to see how the laser gets deflected as a result of the local magnetization. This is all on the order of about 10 microns in scale. We have about, that should be 50 micron lateral resolution. To look at these things from a magnetic standpoint, and very excitingly and kind of in a tantalizing way, when we're at zero field, we see a stripe domain, which was to be expected. But at 200 Gauss, as we move up this hysteresis loop, we start to see the onset of lots of tiny little dots. And these tiny little dots could potentially be an array of skyrmions. And then if we go up a little bit further, we see less and less dots. This is really preliminary data, but it's at least indicating that we may have the presence of skyrmions. And so there is other recent data that's basically mimicking exactly what we've shown now. So we have some good feelings about being able to actually create isolated skyrmions that look probably something like this graphic here, that are in some type of hexagonal array. So the question that we're asking ourselves now is, can we actually just do this in a reliable way and actually produce a single isolated skyrmion? So in the last couple of minutes, I just want to talk about how would we move these things around, right? That's a part of racetrack memory, is that we want to be able to move these things And for this, we again have a ton of knobs to play with. We could mess with anisotropy, the exchange coupling by changing the material, the shape of the system. But the three main ones that people are thinking about are using the Zeeman energy, i.e. use an external magnetic field, use some type of spin transfer torque, i.e. use a current, electrical current, or by using strain through the magneto-elastic effect. So the experiment will look something like this, where we're going to kind of pump the system to do something with the skyrmion. And this could be a photon pulse, a field pulse, or a strain pressure pulse. And then we'll probe it in some way, either with maybe MOC or MFM or something similar, to see kind of what's happening with these skyrmions. And they have very distinct behaviors that we can kind of look for and identify. And one I wanted to show that, which I think is really kind of cool, is that if people use current, and this is kind of the way people are doing it right now, is that you can imagine now if I shoot in an electron, and the electron's going to have a spin to it, it is actually going to have a torque-like interaction with the magnetization. Right? And so it's going to transfer some of its torque to the magnetization, and so it's going to help push it in a particular direction. But as a result, the electron's going to get a kickback and actually lose some of its kind of momentum. And so this is often referred to as something like a spin Hall effect. And for skyrmions, this becomes what's known as the topological Hall effect. And it really resembles the Magnus force, right? So the Magnus force has this idea that if we have something rotating, and in some sense these skyrmions feel like they're rotating, that because of that rotation, we'll get this lateral motion. And so this is exactly what they see in skyrmions, is that electron flow goes one direction and the skyrmion itself goes the opposite direction. And we start to see this topological Hall effect. Turns out this is a potential problem because it wants to run to the walls of the wire because it starts moving around. So people are trying to get around this problem. But there's also a lot of promise. It turns out skyrmions tend to go around obstacles if they see them. They use really low current densities compared to domain walls. So there's a lot of promise in using skyrmions to make all of this happen. So in the interest of time, I'm not going to talk about all this, but there we go. That was goal 3. So I'm just going to go ahead and conclude. So what I hope you got out of this was that we would like to improve the ability to store information, store data, and manipulate data, and work with data. And one possible way to do that is topologically protected and kind of has really longevity for storage is through these topologically protected spin structures, most notably the skyrmion. It could also be that we use domain wall logic, and that's a possibility too, but these skyrmions are really taking off. We do have some knobs to play with so that we can actually create skyrmions and control them. And then I didn't quite get into this, but we have some ideas of how we might be able to push these things around the racetrack memory. And so we have some projects coming together. So before I let you go, I did want to give special thanks to Dr. Haddix. It turns out I have quite the history with the Haddixes, so I thought I'd point it out. First off, I went to Doane College, which actually is where George got his start as a student. He's actually best friends with my uncle Jack, and they've been friends since kindergarten. They went to Omaha North together. They went through high school together, and then they also went to Doane together. They met their spouses together at Doane. So I've known the family for a long time. They also served on the board at Doane for many, many years together. And so these are my kids in front of George and Sally Late Life Recreation Center, which sits on the Doane College campus. He's been involved with scouting. I've taken my kids to his processing plant to see their robots. And so I've had a great history with the Haddix family. And so I was quite honored to take his money for this sabbatical, but I did really enjoy it. I'd also be remiss to not talk about all the different people who helped me and funded me to make this sabbatical happen. In particular, the Nebraska MERSEC paid me to do this as well. And so it was really fun to kind of be able to work at UNL and work at Creighton all at the same time and make it happen. So thanks for your attention. I apologize, I went a few minutes long. I'd be happy to take any questions.
I got one.
Go ahead.
So when you were mentioning that you could play around with the exchange knob,
Yes.
you said that the material you used is cobalt, which is a ferromagnetic material. Why didn't you use things like nickel or iron, which are also ferromagnetic materials, and also why elemental and not an alloy?
Yeah, so it's a great question. So we chose cobalt primarily because it's easy to manipulate its perpendicular magnetic anisotropy, which is the other knob we were playing with, which I screwed it over. So that's the primary reason. We are now considering doing cobalt nickel, which has a similar effect. The ultimate material that's kind of emerging is an alloy, and that would be CoFeB, so cobalt, iron, boron, which seems to maybe have the best potential to create skyrmions. So I foresee that in the very near future, we're going to transition from cobalt, which is a very kind of simple prototype material, to CoFeB, which would be kind of a more relevant material. Okay, good question.
Maybe a basic question. So you showed the result. It was a very preliminary result where you cranked up the magnetic field and the dots went away.
The dots went away.
And I think this is probably really basic to what you're doing, but could you explain why the absence of dots would indicate presence of skyrmion?
It doesn't itself. Only in the sense, so what was probably the most tantalizing thing would be this MFM image, which was where we saw individual kind of dot-like structures. And so these would likely be the individual skyrmions themselves. The question that comes after that is, can we actually isolate maybe single skyrmions or position skyrmions exactly where we would want them, which we're far away from, I'll be honest. But this idea that what will happen as we move up this hysteresis loop is that we should start annihilating some of these skyrmions, basically. And so as they're being annihilated, we'll be left with kind of a lower and lower density of skyrmions, to the point where we might be able to tune somewhere along this hysteresis loop where we might have one skyrmion or two skyrmions or something similar to that. And so that's where that kind of number comes from, and that we have something that's super high density, seems to be almost hexagonally closed packed of these, potential skyrmion structures. But we can actually, with field, kick some of them off and start to see isolated ones, which was ultimately our goal.
Okay. Yeah, I actually have a question from Dr. Duda.
Hi, Dr. Duda.
He is wondering, how are skyrmions similar or different to vortex domain walls?
Yeah, so this is like a big question, I think, and in some ways they behave in almost all the same ways, and so a lot of the physics ends up being about the same, and so the distinction is quite nuanced in that when we talk about magnetic vortices, they don't necessarily have a topological winding number of 1 or -1, and that's the only real distinction. And so for those who don't know a vortex, it's basically like if I took, it can still have a core, but essentially if I have a donut of magnetization, I'll tend to see the flux go around, or the magnetization go around that donut. And so it has some real similarities, but it's not necessarily a topological thing itself. Now, it's very stable because it's either going to have a right-handed chirality or a left-handed chirality. What ends up happening is that in those cases, it usually involves a lot of patterning and other types of things. What we're hoping to do is avoid some of those patterning issues and find an actual object that has this topological stability.
Great. Thanks, Andrew.
I heard you. Okay, so when you were talking about like the topological chirality or the vortex kind of effect, you're kind of like, I guess it kind of relates with, what you were saying about quantum computing, where you're 1 and 0 essentially. Was it when you generated those like half skyrmions, that like another way of like doing that like on and off kind of effect, or no? Like the 1 and the 0. Yeah.
No,
No. Okay.
but I understand why you would say that. But-
Yeah. 'Cause-
So a distinction that should be made is that even though this topological winding number is quantized, it doesn't necessarily mean it's a quantum number.
Okay.
It just happens to be that it's quantized.
Okay.
And so there is some issues of distinction there, even amongst, it seems, the community.
Okay.
So I failed to mention this, but now I will. Or at least I alluded to at the beginning. So all of these things I've told you today were completely new to me. And if actually you looked at my card really closely, I became an affiliate faculty member at UNL a year ago yesterday. So everything that you've seen, I had to learn in the last year, which is actually pretty exciting and really fun. So I got to learn about these topology issues and magnetic vortice issues and all these kinds of fun things. I knew magnetic vortice, I had never thought about Skyrmions. But so this is more like for the student that if you just devote your time for one whole year, you can learn a whole new field of physics. So not necessarily well, but reasonably well.
All right, any final questions before we wrap up? Anybody at home?
And if you ever want to know how strain can manipulate magnetism, that's what I skipped.
I'll do the one more question. So you alluded to it at the beginning, and then you didn't talk about it much in the slides, but tell me about size.
Size, yeah. So this has probably been our biggest bane and problems, right? So I referred to anisotropy as kind of being the clamp, if you will. So what's going to dictate, how hard we're going to pull either side of these things. And then the DMI will dictate, how tightly wound they'll be in those rings. So it's really those two knobs that will dictate the size. So we wanted to detect these things optically using the Moke effect, because that makes our lives much easier. And so we decided to use something that would have really weak DMI so that these things could kind of spread their wings. Anisotropy, we essentially tuned to go to almost 0. So again, the clamps were kind of loose, with the hope that these things would just get bigger and bigger and bigger and bigger and become optically detectable. Ultimately, what we're finding is that that's a really hard problem to do without making a topologically trivial bubble domain. So now we've transitioned to try and do magnetic force microscopy. And by adding all that dipolar coupling and really having this strong anisotropy, maybe cranking up the DMI a little bit, now we're talking about like tens of nanometers. And if we wanted to, we could go smaller. But for MFM, I would like to keep them maybe around 50 nanometers. So these can get really quite small. So when we talk about racetrack memory, these racetracks can be of order kind of 50 nanometers wide. So they'll be exceptional.